Okay, so this is a combination here of the metric system, just a real quick history of the metric system and some of the things that we're going to encounter, as well as looking at scientific notation and dimensional analysis. So here is the little shortcuts that you would find on the back of the newspaper on Sunday mornings. I found this a couple of years ago and thought it was kind of cute. The metric system, where did it come from? How did we get it? It's an interesting story, and it begins back during the time of the French Revolution. At that time, the people in France were going to market and having to use different measures. So they would go and say, for lack of a better term here, they'd go to the grocer and get a pound of wheat, and then go to the jeweler and get a pound of gold. Well, the 2 pounds wouldn't be the same. They would go another mile down the road and get a gallon of milk, and then go get a gallon of water. They would not be the same. So over time, this took its toll, and so the French government decided to get a commission together, which they did, and determined that they needed to fix this particular problem for trade so that we could have trade all through the country. The metric system, as I said, was during the French Revolution, or actually was kind of born along the same times, and that was going to pose some problems, as we'll see here in just a little bit. So two guys were commissioned, two astronomers actually were commissioned to measure the diameter of the Earth. It was determined that the meter, the length of measure, needed to be a length that was universal, that not just people in France would use, but it would be used throughout the world. And so they would need to use something that was not specific to France. And they decided to take the Earth from the equator, as you can see here, from the equator all the way up to the North Pole, the diameter, or a portion of that, and divide that by 10,000 to get the length of the meter, a standard value. So they did that. And so what they did, they took two guys by the name of Delambre and Michan. One went north and the other one went south from Paris. As I said, there's a meridian, which is a straight line that runs right through France. So right there, runs right through France. And they decided that they were just going to take that little arc and extrapolate that all the way down to the equator and all the way up to the North Pole. So they needed to measure this very accurately. And so these two guys did that. They went north from Paris and south from Paris down to Spain, down here to Barcelona. So here's Paris right along in here. See that? There's Paris. Here's Dunkirk, and down here is Barcelona. So they had to measure that distance, and when they did that by using towers and triangulation. And so we'll talk about triangulation a little bit later, but just remember when we get to this, a guy by the name of Snell, Willibrord Snell, devised the method of using triangulation here. So it took them 8 years to go from France, from Paris, France, to Dunkirk, and from Paris down to Barcelona. Well, again, as I said, part of the problem was the French Revolution was occurring, and that kind of slowed things down a little bit. But they eventually got it going, and that produced then the metric system, or it actually gave them the basis for the metric system. So what that ended up being was the length unit, and they called that the meter. The length unit is now defined as the distance that light travels in 1/299,792,458 seconds. That is the reproducible unit. All of the standard units, except the kilogram, as you'll see, have a non-physical definition. And so here is the meter. If you were to go to France, in Sèvres, France, just outside Paris, you would see this meter. So you can take your meter stick up, and there's two lines etched in this bar that will show you the length of the meter. That is the official meter. The standard unit of time, the base unit of time, is of course the second, and originally it was defined as 1/86,400th of a solar day. So there's 24 hours in a day, 60 seconds in a minute, or 60 minutes in an hour, and 60 seconds in a minute. You know what I'm talking about. Multiply those out and you'll get 86,400. That's a very good number to know, 86,400. So say that again. Right, 86,400. Mean solar day didn't really work in terms of being very precise over a long period of time. So it is now defined as the time taken by cesium-133 to vibrate 9,192,631,770 times. Somebody sits there and actually counts this little thing as it vibrates up and down that many times. It's a boring job. Here's a little humor. I got you 10 roses. I believe strong relationships are based on the metric system. I know it's not that good, but I thought it was funny. Now, the standard unit of mass is the kilogram. Not the gram, but the kilogram. And I've got a video for you to watch that I'll link as well a little bit later about the kilogram. It's interesting, and they're trying to come up with a way to have a non-physical standard that the kilogram is. But they don't have that yet. They're working on it. It's very difficult. But anyway, so what they have is a platinum iridium cylinder, and it is under lock and key, but very specific temperatures and very specific pressures so that it does not absorb any type of other molecules to change its mass. They don't want that to do that. So what we have here is the base units. This is what you need to know. The base units are the meter, the kilogram, and the second. Those are the base units. Those are the fundamental base units. There are others, but these are the ones that we're going to be using. Here are some more base units. As I said, Kelvin degree. You know that one. It's the absolute degrees. You've used that. The amp, Coulomb per second. That is a base unit. The amp. A mole. You know that a mole is an amount of substance. 6.02 times 10 to the 23. When is mole day? Mole day is October 23rd from 6:02 a.m. to 6:02 p.m. So we'll celebrate that. It's a fun day. Others would be the light intensity. The candela is light intensity. And we'll get to deal a little bit with the candela, but not much. But you may have seen it, especially on high-powered flashlights and those beams. Those are what it's called, Q-beams. So we take the base units and we combine those into what are called derived units. These are derived units. So the base units combine to form the derived unit. And so for example, speed is meters per second. Speed is meters per second. That's length, the base unit for length, which is the meter, divided by time, which is the base unit for the second is the base unit for that. Volume is length times width times height. Length times width times height. So right there you can see that those are all length units. This is volume is meters times meters times meters, or centimeters times centimeters times centimeters, which is centimeters cubed. Force is Newton. The Newton is the unit of force. We'll get to that quite a bit. You'll have to know that the base units are also the kilogram meters per second squared, and then acceleration is meters per second, or meters per second squared. Here's a chart showing you just a lot of the derived quantities along with their symbols. So here it is in terms of their base units. So if we take all of these and break them down to the base units, that's what it looks like. That's kind of nasty to look at. That's why we use these types of units right here. So here's a question. Which is the fundamental unit in this list? You have a millisecond, you have a meters per second, seconds per meter, a meter, or a meter per second squared. I'll give you 3 seconds. You got it. It's D, the meter. That is the fundamental unit here. Next question, what is the derived unit? Possible answers are the kilogram, the second, the meter per second, the meter, the candela. 3 seconds. You got this one too. C, meters per second. These are all fundamental units, even though this one is not as common as the one that we're going to be using. We're going to be using the meter, the kilogram, and the second. The candela is light intensity. So scientific notation, real quick refresher on scientific notation. It's a method of expressing very large numbers or very small numbers. And we want to do that because putting those into the calculator takes a while, or trying to multiply those things takes a while as well. But we're going to express this between a number of between 1 and 10 exclusive. And by exclusive, I mean we're not going to count 10. So we're going to go from 1 to 9.99999. So we won't get to 10. And then some whole number power of 10. All right? And then, of course, we have orders of operation that we have to include with this. We'll talk about that here in just a few moments. So let's take a look here. Let's look at some numbers, put them into scientific notation. I've divided these things up, and in fact, this is the standard way of doing things internationally when we are looking at large numbers. Instead of using commas, we're going to use spaces. And so here we have 3, 6, here's the distance to the nearest galaxy, which is Andromeda, and it's 3, 6, 9, 12, 15, 18, 21, 22. So the scientific notation is 2 times 10 to the 22 meters. So if I were to take 2, multiply it out by times 1 times 10 to the 22, I get that distance. Radius of the Milky Way galaxy. How big is our Milky Way galaxy? It's 6, and then 3, 6, 9, 12, 15, 18. So 6 times 10 to the 18 meters. Okay? All right, you do the galaxy, the mass of the Milky Way galaxy. Go. I end up with 2.2 times 10 to the 41 kilograms. 2.2 times 10 to the 41 kilograms. I need to, we come here, we're going to have one digit left of the decimal place. Mass of the Earth. Go. Good. 6 times 10 to the 24 kilograms. Distance to the nearest star, Alpha Centauri. .3 times 10 to the 16 meters. Distance of a light year. 1 times 10 to the 16 meters. So if 4.3 times 10 to the 16 meters is the distance to Alpha Centauri, and 1 times 10 to the 16 meters is the distance of a light year, how many light years is Alpha Centauri? 4.3 light years. That's how long it takes light to travel from Alpha Centauri to the Earth. All right, so here now let's turn this around, looking at the other direction. This is the radius of a hydrogen atom. Now we're going to move it in that direction. We're going to move it that direction. So we're going to go take the decimal point and move it 3, 6, 9, 10, 11. So this is 5 times 10 to the negative 11 meters. Do the same thing here with the radius of a proton. 3, 6, 9, 12, 13, 14, 15. So this is 1.5 times 10 to the 15 meters. negative 15 meters. Don't forget that negative. It's not a negative number, it's just a number that's less than 1. You do the mass of a speck of dust. The mass of a speck of dust. Go. (6.7 times 10 to the negative 10 kilograms. Mass of a proton. (1.7 times 10 to the negative 26 kilograms. There you go. You'll have plenty of practice with those. So now let's take these and expand this out. The age of the Earth is 1.3 times 10 to the 17. So we're going to take this guy and we're going to move him 17 places. We're going to move him, he's going to move 17 places. So this is going to be 1, 3, 0. And that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 seconds. So you see why we use scientific notation. That'd be a mess to have to write that all the time. And then you can do that one with the period of the Earth's revolution. Three, 1 with another 6 zeros. 1, 2, 3, 4, 5, 6 seconds. Period of a typical satellite. 5,100 seconds. So taking this in 1, 2, 3. So we end up with 2 zeros. Now the half-life of a neutral pion. Now we're going to move the other direction. And so since we already have one that we have to go through, all we need to look at is and add 15 zeros in front of that. So that's going to be 0.000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 2 seconds. I'm glad we have scientific notation. Now, there's something that you will run across occasionally called engineering mode. Not going to do much with it here. Essentially what it is it has the multiples of 3 as being our exponent. So 10 to the 3, 10 to the 6, 10 to the 9, 10 to the negative 3, 10 to the negative 12. So this would be using, for example, 400 times 10 to the 6. Instead of using proper scientific notation, engineers like to use a way to compare numbers with the same exponents. So it just kind of gives them that ability.